So, we talked in class about the product rule, and I told you what it was. I told you that the derivative of f of x times g of x was, for some reason, equal to f prime of x, g of x, plus f of x, g prime of x. We were taking a derivative one at a time and multiplying by the other, and then we added those two things together. Now, the question I want to talk about today is really why this is true. Why derivative rules are true in general. So remember, the derivative comes from this definition, the limit as h goes to 0 of f of x plus h minus f of x over x plus h minus x. In this case, the derivative will be f of x plus h, g of x plus h, right? That is the function we want to take the derivative of f times g at x plus h minus f times g at x over x plus h was the x coordinate here, minus x. And again, usually this is simplified to be simply h, because x plus h minus x, usually you'll see those crossed out, and so it becomes just h on bottom. So I'll leave that here, a little bit of board magic, that's fine. Now the question is, how do we get from this to that? Well, I could show you there's some algebra that works. So let me show you the algebra that works. This is the limit as h goes to 0. I'm going to do something a little bit funny. I'm going to add and subtract something. F of x plus h, g of x plus h, plus f of x, g of x plus h, minus f of x, g of x plus h. And then we've still got this minus f of x, g of x. So it looks like I used a lot of room, right? All of this is over h. And we can go ahead and split that into two fractions over h, because if we were to subtract these, we would, or like if we were to add these, we would add the numerators, right? I'm going to swap these. I actually want to do minus here and plus here. But that's still, so why can I do this? Why can I subtract f of x, g of x plus h and add it? Well, minus 2 plus 2 is 0, right? Minus 5 plus 5 is 0. This number and this number are exact opposites, minus and plus. They will cancel out exactly when we add the numerators. So that's a little bit of algebra. Now you might say, why did I do that algebra? Because now I can suddenly factor something out here. I can factor out the g of x plus h, and I'll have f of x plus h, g of x plus h, or I'll have f of x plus h, minus f of x, right? F of x plus h minus f of x, both multiplied by g of x plus h, all over h, plus the limit as h goes to 0 of f of x, g of x plus h minus f of x, g of x. So the common thing here is now the f of x. So I'll pull the f of x out, and I'll get g of x plus h minus g of x over h. Do you see it yet? This part, g of x plus h, this is going to g of x. Let me use a different color here. So this is going towards g of x. And then this part, that's the derivative of f prime of x. This part here, that's my f of x. And this is the derivative g prime of x. Once we plug in h equals 0, g of x plus 0 is g of x. This limit is 0 over 0, and it goes towards the derivative. Between these things, we are adding them. And that is exactly the product rule, just written slightly in a different order, right? I wrote g of x f prime instead of f prime g, but 2 times 3 and 3 times 2 are the same. These two things are the same, and then these two things are the same. So this is how the product rule, how we would prove it. This is actually a really nice, short, clean proof. The only thing that's a little bit mysterious here is why the heck, how do we come up with that idea of adding and subtracting something? Well, the way that I like to actually think about that, there's actually another way to think about all of this together, and that is actually to think about what this quantity up here means. F of x plus h, g of x plus h, minus f of x, g of x. So this is a second proof now. We've already seen one proof, one demonstration of why it's true. Now I'm going to show you another way that's maybe a little bit more intuitive, but a little bit more intense as well. So f of x plus h, g of x plus h. If you remember from grade school, 2 times 3, we could represent as 2 by 3. right? So 2 dots on one side, 3 on the other, and then we have this grid, this rectangle, right? Counting the dots, you can also think of this as an area, 2 by 3, and the area here is equal to what the product is. So this is a product and that's a product, and so what we're doing is we're finding actually the area between two things and subtracting them, right? So if I have a rectangle, let's call this side f of x and this side g of x. And then if I make this part of a larger rectangle, and we're going to call this side g of x plus h, and this side, the big side, the tall side here, f of x plus h. Well, now we see that the big red area is f of x plus h, g of x plus h. The black area for this rectangle, that's f of x, g of x. So what we are interested in then is this difference, is the difference between the areas of the big rectangle minus the small rectangle, which will be this area. I'm going to split this into 3 little sections, this area and this area. So what we could actually do is we could rewrite f of x plus h, g of x plus h minus f of x, g of x essentially in this way. This blue region up here, this has length g of x. And then the height here is actually the difference between this long red side and the short black side. So that'll be f of x plus h minus f of x. This tall blue side over here has height f of x. And then the width is the difference between the long red side and the shorter black side, g of x plus h minus g of x. Plus this tiny little rectangle, which is these 2 smaller parts, the f of x plus h minus f of x, g of x plus h minus g of x. So this whole thing is equal to f of x plus h, g of x plus h minus f of x. And if you were to actually multiply all of this out and simplify, you would get that. But now we can actually think about how to do this using area formulas, length times width. Now remember that all of this is divided by h, so if I divide this stuff by h every single term, divide by h, and divide by h, I can do either of these two, right? Because I can divide the whole thing by h and I can kind of like distribute that to one of them because it's multiplication and division are all at the same level, right? So here's again my f prime, here's my g, here's my f, here's my g prime, here's an f prime, and then here's g minus g. That's just 0. So this piece is going to 0. This little corner here is actually going to 0 as h goes to 0. That's going away. But what we're really seeing is that when I make the rectangle bigger, one portion of that is proportional to g of x, and then the height of that, so the length of this is g of x, the height here is like my df, my change in f, that's my f prime. So think of this as the g times the small change in f, f prime, and then this region over here, this is the height of f and the width of that small change in g of x, which is the g prime of x. So that's really where those actually come from if you want to think about it geometrically. I love thinking about stuff geometrically, so I think it's really cool. We can do this with algebra, or we can show where the algebra comes from with a picture. Anyways, that's what I wanted to say about the product rule.